Let's look at how Newton's second law would be applied in different coordinate systems. In Kinematics of Particles module, we talked about three primary coordinate systems. We talked about Cartesian coordinate system, we talked about polar coordinate systems, and we talked about tangent normal coordinate system. So if you were analyzing the motion of a particle in any one of those or more coordinate systems, the question is, how would you apply Newton's second law? So let's start with Cartesian coordinate system. Cartesian coordinate system. Let's say we have a particle moving along a curved path, okay, and we have a reference frame, which is a Cartesian reference frame. And we know something about its acceleration. So let's say its acceleration is given as a, then we can write some of the forces acting on the particle equal to mass times acceleration. So if you draw a free body diagram of P, and remember you're always showing it as a particle, sometimes you may draw it as an object also, but all the forces are shown to be concurrent with 1 point. Okay, so there may be one force F1 like this, another force like this, another force like this. They're all concurrent, and we will resolve these forces in our chosen coordinate system, and we would write the right hand side as m times acceleration along x direction plus acceleration along y direction, assuming that this is moving only in an xy plane. And that would be the right hand side, right? On the left hand side, we will have some of the forces along x direction, I hat, plus some of the forces along y direction equal to mass times ax I hat plus m times ayj hat. So this is clearly a vector equation, and you would obtain two scalar equations from this equation by equating the coefficients of I hat. So sigma fx should be equal to m times ax, and sigma fy should be equal to m times ay, right? And that would give us two scalar equations. So sigma fx equal to m times ax and sigma fy equal to m times ay. So from these two scalar equations, you will be able to solve for two unknowns, right? So there may be some forces that may be unknown, maybe some part of the acceleration that may be unknown, and you would be able to calculate at most two unknown variables from this equation. Something similar can be done with other coordinate systems as well. So let's say we have tangent normal coordinate system. That's our number 2 that we're discussing. So in tangent normal coordinate system, we again have the particle which has a certain velocity, could have some acceleration, but this time we are going to be resolving everything in terms of tangent normal coordinate system. So we have ETs and we have E and hat. So sigma F equal to MA, of course it still applies, and this would be sigma Ft along tangential direction plus sigma Fn along normal direction equal to m times acceleration is also along tangential direction and normal direction, right? So we already know what these things look like in tangent normal system, so we can write that. Again, this is a vector equation, so we will resolve it, and this would become MAT, which is m times v dot. That's number 1 equation. Then along normal direction we have sigma f, and that is equal to m times an, and that is equal to v squared over rho. So those would be the two scalar equations that you would have for tangent normal coordinate system. Again, you have two equations, so you can solve for at most two unknowns. The third one is polar or r theta system. And in this system again, we have sigma f equal to m times acceleration, and sigma f can be written as sigma fr er hat plus sigma f theta e theta hat. So we're resolving the forces along radial and tangential direction, and right hand side is m times ar er hat plus a theta e theta hat, and that is equal to mar er hat plus m a theta e theta hat. So vector equation, let's resolve it along er hat and e theta hat direction, and we get sigma fr equal to m times acceleration along radial direction is r double dot minus r theta dot squared, and along theta direction it is m times 2r dot theta dot plus r theta double dot. So once again, at most two unknowns can be solved from these two equations. So if you look at these three coordinate systems, the Cartesian, the tangent normal, as well as polar, it's clear that these laws, these equations, they look some sort of balance laws, right? So you have a left-hand side and you're trying to balance it with the right-hand side. So on the left-hand side, you have the force, on the right-hand side, you have mass times acceleration. And that's why some textbooks and authors refer to these equations as balance laws as well, because you're balancing things on the left and right-hand side. In statics class, the right-hand side was almost always zero because there was no acceleration, there was no movement, but that is a temptation that you would have to resist from this point onward, where you make the right-hand side to be equal to zero. So unless you can confirm that acceleration is zero, please don't try sigma f equal to zero in any case.